Hi, I'm Rini. I work as an applied scientist in Amazon, and I work in the field of speech processing. Specifically, I deal with automatic speech recognition. You all must have heard of Alexa, right? A voice driven bot. This is where my expertise lies in. And over the next few hours, we are going to look into what this voice driven future of AI is like. We are going to peel back the layers of what is the intersection of two of the most powerful and transformative technologies in the field of artificial intelligence, namely large language models and speech. Let us go over what we will look at in this masterclass. I will begin by introducing you to some of the terms that are important in this technology. We will then move ahead with looking at how AI agents can be built in the speech domain. We will also look at how we can fine-tune these models, how we can include information from the external world, how we can model multi-agent systems, and much more. We will also have some hands-on lab where you can see what all this technology is capable of doing. Have you ever tried talking to a voice assistant and the assistant ended up playing tunes from NTV instead of news from NDTV? It happens. But somehow, all of this is in the past. With the rise of LLMs, such mishaps do not happen anymore. With greater technology comes greater power. Let us dive in and look at what happens in different blocks of this technology. But before we do so, let me ask you a basic question. Why are we even concerned about speech in this era of AI? Why does speech matter? Well, speech is one of the most naturalistic form of communication. It is the oldest form of communication that one has. Before these GUIs, chatbots, and textual data exchange, people used only their voice to communicate. Therefore, not only is it most naturalistic, but also it is one of the most powerful modalities of communication. In this age of AI, speech is not just about convenience, but it is also the core modality of multiple AI systems. Let's think about some smart assistants, right? We have Alexa, Google Assistant, Siri. They all work based off speech. We have customer service bots, voice typing tools, real-time translation. All of these are also based on speech. The market for speech AI is exploding. But the question is, how good is it? Most of us have tried voice-based assistants, but are we 100% satisfied with it? It is not because speech tech is bad, but because it's evolving. Speaking of evolution of speech tech, let us look at how speech has come a long way, starting from the 1990s to the 2020s. The very first speech recognition system was basically a system designed to only understand digits from 0 to 9. This is something like the voice bots that we used to have back in the day. We have to press 1 for billing, say 1 for billing, or say 2 for refund. And only those finite vocabulary words could be recognizable. So starting in the 1990s to 2010s, there were a lot of HMM, which is Hidden Markov Model-based speech recognition systems. These work on phoneme recognition. Phoneme is basically a small unit of speech, and these models try to recognize where these units occur and put together these units to find out what the user is trying to convey. They also had some very regular rule-based set of NLP techniques. Come 2015, we had the rise of deep speech. These were the early end-to-end systems, and they tried to model speech in an end-to-end fashion. Here we are in the 2020s, and we have Whisper, GPT-4, and so much more that not just understand speech, but also the context behind it, the intent behind it. They have a context-rich vocabulary, and they not just look at what you're speaking, but also what you spoke and what you might speak. Let us break down the blocks of a traditional ASR system as well as a modern LLM-based system and see how they differ in terms of these blocks. Firstly, with respect to ASR or automatic speech recognition, the traditional systems involve a hidden Markov modeling wherein every phoneme and the next phoneme is modeled in terms of transition probabilities. How likely is the next phoneme to occur given the previous phoneme? And these probabilities are modeled from a huge amount of supervised data. Coming to LLM-based systems, we now have end-to-end modeling wherein we don't have to worry explicitly about these state probabilities or transition probabilities. Speaking of the NLP layer, as I mentioned, this is very rule-based, statistic-heavy layer in the traditional ASR systems. In the modern ones, the transformers and LLMs like GPT, we do not require to specify such rules explicitly. Let us look at how dialogue management happened. In the traditional models, we had predefined flowcharts. If the user said this, do this. If not, do that. But now with LLMs, we do not have to specify a flowchart like that. The LLM can identify the intent and do what is required by themselves dynamically. As I said, context awareness was not present in traditional AI systems or was very minimally present. Now we have heavy contextual awareness. Speaking of language flexibility, we had a very fixed vocabulary and a narrow vocabulary of words in traditional ASR, whereas the limit to modern day LLMs is endless. So, speaking of all of this, let us look at a small demo as to what these modern day LLM-based speech recognition systems can do. We're going to take a real example of how we can give the LLM a voice command and ask the LLM to infer from it what we intend to do. Let us go and look at the demo. In this demo, we'll be taking a raw audio waveform and we'll try to transcribe it using Whisper and use this transcription to generate insights about what was said using ChatGPT. This demo will demonstrate the power of an LLM in turning a voice command into a structured prompt. Let's look at the demo. We will first install the requirements. We need OpenAI Whisper. We also need some sound-based libraries to process the audio or to record one. So here we import Whisper. We then load the base model. There are multiple models in Whisper, which is tiny, small, medium, and here we are using the base model. We also have a recorded audio file here.
Hey, can you schedule a meeting with Dr. Rao next Friday after lunch and email the agenda to the team?
You can always feel free to record one on the go to have a more user-friendly interaction. And then we try to transcribe this. So this is just a single line command where we use model.transcribe and the model will then convert your voice message into text. So here we see that the transcription says, hey, can you schedule a meeting with Dr. Rao next Friday after lunch and email the agenda to the team? Now, if you had a personal assistant who you give this voice instruction to, they need to find out that there are multiple things that you want them to do and do things accordingly. But can a machine do that? Can a machine understand that from your voice? Let's look at the next part. So here we have the prompt that we give to ChatGPT. We tell ChatGPT that you are an assistant that extracts action items from user messages. And then we pass the transcription that we have obtained from Whisper to ChatGPT. And here we see that ChatGPT returns the action items as two things. One is to schedule a meeting with Dr. Rao next Friday after lunch. And the second is to email this agenda to the team. It's very clear. And now we've gone from just voice to a very structured action item. And we can also ask ChatGPT to extract the participants or other items of interest to you. Here you can see that it has clearly identified from your voice that the participants are Dr. Rao and the team. Well, we've successfully transcribed what you've said, and we've also generated actionable insights from them, thanks to the power of LLMs in speech. So, in the previous section, we saw how we went from voice to text to meaning in just a few seconds. And behind every good transcription, there is a beast of a model. In our demo, we saw that beast was Whisper, OpenAI's open source ASR system. Now let's dive in and break it into pieces to see how Whisper is doing such a great job. Let us look at how we can go from sound waves to text from a bigger picture. Taking a step back, in the traditional ASR systems, we had separate modules doing separate jobs. For example, we had the start of the function with an audio pre-processing module. This module will basically clean up your audio, remove background noise, and do anything it requires to make the audio a better version of itself. The next part is the acoustic modeling part. In this part, we have the MFCC features typically, which are the MEL scale features that we typically use for ASR systems, and the HMMs. The HMMs will model the phoneme, will see what characteristics and signature of the phoneme stand out, and model the probabilities of transition between one phoneme to another. The next block is the lexicon and language modeling block. In this, we have n-gram-based models with certain rules that model the language in it. And finally, we have the decoder that glues everything together. Now, this is the pipeline of a traditional ASR system. Now, Whisper enters with its end-to-end pipeline, where we just have to give it the audio as the input, and it will give us the text as the output. Now, let us look at what this end-to-end pipeline is actually doing. So, what is Whisper? Whisper is a large language model trained on 680,000 hours of supervised data. Why is Whisper special? Because it's not only trained to do transcription, but it can also do other tasks like multilingual detection, translation, and transcription in real time. It is also robust in noisy conditions and can recognize 96 different languages. Can you imagine how much of compute that would be if we want to achieve that using a traditional ASR model? When we look at the Whisper architecture, we see that it has an encoder and a decoder. The encoder takes in spectrogram as features. You can think of spectrogram as a basic heat map. The areas where you stress while producing voice is stressed on the heat map or the spectrogram as well. So every syllable or every phone that you pronounce has a specific spectrogram that is its signature. These input features are taken by the encoder to generate an embedding. The decoder, on the other hand, does not just focus on the current embedding, but also looks at contextual embedding. It takes into account the whole context and tries to produce the token, in this case, the transcription text. So let us look at what all Whisper can do with respect to translation and transcription. We will now open the Whisper web app. To make it more interesting, let's record in real time in one of the native Indian languages and see how Whisper can convert it into English. So here we see that Whisper large V3 model is used, and there is a record option here for you to record and try, and we can either transcribe or translate. Let's try the translate one. I will be recording a phrase in Hindi and try to translate in English in real time. मौसम अच्छा है. So let me play what I just recorded. मौसम अच्छा है. Okay, and now we want to translate this to English using the Whisper model. We can observe how this handles context, tone, background sounds, and so much more. You can also try recording in a noisy environment to see how it can denoise and still get the content out of it. It takes a while for the transcription to be visible, but let's wait it out. I also want you to pay attention to how well it can handle the context. Is it accurate? Is it able to transcribe what you just said? Is it able to translate them well, including the context and meaning? Is it able to identify if you have used sarcasm? Also, is there anything that surprised you with respect to the translation or the transcription? I also want you to take a step back and think how traditional ASR model would be able to handle this and what the latency would be in that case. So here we can see that in the output, it has clearly transcribed it as the weather is good. A very good translation as well as transcription here. To summarize, we saw that Whisper is a large model that does all the processing that a traditional ASR would do in an end-to-end fashion. It can talk and understand in your language, and it is able to denoise as well. It is also very easily integrated with just a few lines of code. The key takeaway here is Whisper doesn't just hear you. It hears you in your language and is fast as well. Now that we've seen how we can put all of this in action, we will now see what the foundations are when we are doing speech processing with LLMs. In this section, we will try to understand the two pillars of listening and speaking capability of the LLM, which is speech to text or STT and text to speech or TTS. After looking at the components of these two pillars, we will move ahead with tokenization. We want to understand how speech is being tokenized and the different ways of doing it. And finally, in this section, we will also look at how we can fine-tune these two pillars. Let us now understand how LLMs fits into both directions of speaking as well as listening. We will also see the deep learning behind the science of sounds and language. When you take STT system, you have three major modeling components. The first is the acoustic modeling. The second is a linguistic modeling, and the third is a language modeling component. In the acoustic modeling component, you basically want to understand what are the phonemes being spoken, what are the basic units of speech, and what are their signatures. You try to identify these from the speaker and model them. The parameters for each of these phonemes are also different from each other, therefore helping the model identify these differences. In the second linguistic modeling block, the model tries to identify which sounds or which words sound correct together. And the final language modeling part identifies in what context these words can be put together. So when you say ice cream for ice cream, the acoustic model is going to hear I scream. But the language model and the linguistic model put together will understand the context behind and will transcribe them as ISCREM in the first part and ICECREAM in the second part. And this is how the hand-holding between all three models happen in the speech-to-text system. Coming to the second pillar, where we are giving machine the voice, the TTS or the text-to-speech pillar has different set of components. The first component is basically a text normalization component. The text that you give needs to be normalized for the model to understand what each part of that text is. After the first process of text normalization, there is a grapheme to phoneme conversion. So the text bits or the units in text are graphemes and the units in sound are phonemes. So we try to map these graphemes and phonemes so that we can move from the text modality to the speech modality. This is also the part that maps spellings to pronunciation. And this is also the part where context is important because depending on the context, the words that have similar spellings may have different pronunciations. The next part of a TTS system is the acoustic vocoding. Here, they take the phonemes that the previous model has given them and they try to generate sounds from these. And the end result after generating these sounds is a waveform that sounds human-like. So let us now look at both the flows of STT and TTS side by side. We can see that we start with the audio in STT, get the spectrogram features, and then process this using the acoustic model and following which the language model. And the final output is text. In TTS, we first take text, we then normalize it, and this normalization also includes the expansion of certain acronyms. For example, you write DR for doctor and kg for kilograms. So these kind of normalization is also happening in the first step of TTS. And then we move from graphemes to phonemes, followed by prosody modeling, where we identify what sort of intonation to put in, and the vocoder that actually pieces these parts together to form voice, and the final audio waveform. So in the last section, we saw how we can go from speech to text and text to speech. But is only transcribing enough? Do we not want to understand the meaning of the transcription? Let's say you talk to a voice assistant and say, "Can you not turn off the light?" Now, this isn't just instructing them, but this also has some meaning to it, some information that is beyond transcription. Now, how do we get this context? How do we understand the emotion of the speaker? How do we put all of these parts together rather than just industrially going from speech to text? This is where the LLMs play a huge role. They are the brains behind the whole TTS pipeline. Let's look at how they do it. Looking at what is the job of a language model in speech. So we saw the pipeline, right? We had audio, we have whisper, we have text, and then the LLM. So what does all of these bring into the picture? What is the value addition that LLM gives in such a context? We see that voice is our input. Whisper takes this voice, converts it into text. And the LLM or the GPT gives the text its meaning, intent, and understands what needs to be done in the form of actionable insights. The LLMs can understand relationships, intent, emotion, and even sarcasm. So, if LLMs are so smart, what is it that are making the LLMs so smart? Let us look at the architecture behind this. The basic concept because of which the transformers are all powerful is the concept of self-attention. Self-attention is basically like a book that remembers your entire story. It has context of what you're speaking, where you're speaking, and how you're speaking it. For example, let us say I say the sentence, "I went to the bank to deposit." Now here, if I'm talking about money, bank here refers to a financial institution. But if I'm talking about fishing, bank here refers to a river bank. The context gives the word its meaning. And LLMs are pro at understanding this because of the mechanism of self-attention. Speaking of self-attention, we know that context is king. Let us look at this example sentence. It says, "The cat sat on the mat because it was tired." Now, we as humans know that it refers to the cat. But how does the LLM know that it is referring to the cat? Because it can also refer to the mat. And this is why it is very important to understand context when it comes to speech. LLMs aren't just parroting text, right? They are understanding the context and they want to give the right output depending on the intent behind which the human is using the LLM for. So let's put GPT to work and understand how it can go from text to reasoning. We will reuse our transcription from earlier. So in this particular example, let's say I have a voice note that has a transcription. I have a flight to New York at 3 p.m. tomorrow, but I think I might have a meeting overlapping with it. Can you help me reschedule it? It is a complex thing where you need to understand what is the intent of the user, and you also need to understand the entities behind it. Now let's look at the function. The prompt that you're going to give to the LLM in order to be able to do this is this. First is the intent. what is the person asking for? And second are the entities. We want to identify any relevant entities such as the date, time, location, and events. Once the transcription is done, it is passed on to the LLM, and the LLM then gives out the following. The first is the intent, where it correctly identifies that the person is asking for help to reschedule a meeting that overlaps with their flight to New York at 3 p.m. tomorrow. The second part are the entities, and the LLM identifies them as flight to New York, 3 p.m. tomorrow, and meeting. In a similar fashion, if we have a different transcription that says, I need to make sure the meeting with John at 2 p.m. tomorrow is still on, and if not, let me know what time works best. This is again another example of a very complex prompt where the LLM has to neatly identify the intent and entities to be able to take the correct action. Here again, we see that GPT has correctly identified the intent and the entities as tomorrow, 2 p.m., and John. We just looked at how LLMs give voice AI their brain by turning speech into understanding. In this section, we will look at the science behind speech by looking into phonetics, linguistics, and acoustics. Did you know that there are 44 different phonemes in English, but over 1,000 distinct acoustic signatures? Let us look into how LLMs can enhance speech to text and text to speech. The first thing is they can help to resolve homophones. It could be there versus there versus there. They all sound similar, hence they are homophones, but LLMs can distinguish between them. Secondly, LLMs can predict long-range context. If there is a big paragraph, somewhere between which says, because I was tired, and somewhere at the end it says, I went to bed early. LLMs, thanks to self-attention, can connect these two. And thirdly, it can guide intonation in TTS. Let's say you say really versus really. The same word, but different meanings. LLMs can help provide intonation context in TTS. This is the reason why LLMs are now being jointly trained with audio during pre-processing as well as post-processing. There are multiple key players in this ecosystem as well. For example, we have OpenAI's Whisper, we have Google's DeepMind, we also have Microsoft's Azure Speech and Levin Labs. Let us now look at how Levin Labs can process an input that you give and infer the emotion from it. So, the basic text that we want Levin Labs to process is, welcome to our voice assistant, how can I help you today? Let us look at this. We paste it in the TTS or text-to-speech portal of Levin Labs and try to generate the speech.
Welcome to our voice assistant. How can I help you today?
Now, you can see the intonation, speed, and clarity and also adjust it according to how you want it to be personalized. Let us try changing the punctuation or adding some emotion cues to it and see how the TTS rendering changed. In this example, we are going to add an exclamation and also include the fact that the assistant is excited about it.
Welcome to our voice assistant. How can I help you today? I'm so excited to assist you.
Now, let's try another example where we change punctuations to get a different outcome.
Welcome to our voice assistant. How can I help you today?
So just by adding the ellipsis, we make the assistant respond hesitantly. We will do another example where just by modifying the text, we get a different emotion. For example,
welcome to our voice assistant. I wish I could do more to help. How can I assist you today?
So here we see that the punctuations, adding ellipses or exclamation marks, can significantly affect the tone. The word choices also make a difference in the TTS rendering. Let us try to do this by ourselves using our notebook hands-on. So here we import Whisper, which is going to be our backbone for TTS. And we will use the medium model. You can use the base, small, medium, or large model based on your resources. The audio file that we will be using here today is basically wanting to call mom. Let me play the audio that is recorded for this particular lab.
Hey, don't forget to call mom, okay?
So here what we do is we try to transcribe the text. And we can see that the Whisper AI model has transcribed it as, hey, don't forget to call mom, okay. Now, we also want to modify this text to create two different versions. One which says, can you remind me to call mom at 7? And second that says, hey, don't forget to call mom. Here we have chosen one of the voice IDs and we want to generate speech. You can also play around with different factors such as stability, speed, and similarity boost. So here we can see that the first transcription is converted.
Can you remind me to call mom at 7?
As this, and the second transcription is converted to.
Don't forget to call mom, okay?
So here we can see that we can build our very own TTS system and we can play around with just text to include the emotion that we require. We just saw how STT and TTS systems work and also understood how TTS can be modified to emotionally sound the way you want. However, emotional TTS is hard. It is difficult to understand sarcasm and regional humor. Now, in this section, we will see how the machines see speech. They don't just see speech as whole sentences, but they see them as parts. And these parts are a result of tokenization. Let us look at how these are being done. When the machine hears an audio or a word, let's say, that says, this is photosynthesis, it just doesn't understand what photosynthesis is. Instead, it breaks it down into smaller pieces. Instead, it needs to convert the spectrogram into smaller pieces, visualize what each of these pieces are, and then predict a sequence of tokens for that phrase. Let us look at an example for the same. Imagine we are given a word, unpredictability. Here in this notebook, we would be importing the GPT-2 tokenizer to understand how this GPT is tokenizing this particular word. We can see that it has broken the word unpredictability into 4 tokens: un, per, predict, and ability. Similarly, you can also tokenize a bigger word such as hyperquantum energy dynamics and see the tokens that the GPT generates. The bigger the word, the more the number of tokens that the GPT can break them into. We also call these the byte pair encoding or the word piece encoding. These are data-driven approaches where they split words into chunks that occur frequently in the training data. Why does this help? Because it gives us a smaller vocabulary size to train in, it handles unseen words, and it also reduces the memory needs. The best thing about these text tokenizers is they work great for text. But the speech models need something that is closer to how we speak, right? And that is where the phoneme-based tokenization comes into picture. Let us see in this cell, we have 2 words, bat and pat. The only phonemic difference between these 2 words are the first, that is the change from b to p, and the word's meaning completely flips. Some models like the Google TTS or the Mozilla TTS map text to phonemes and then use these to generate text. And this is how the tokenization is done. Others like Whisper infer phoneme-like tokens implicitly from the audio spectrograms itself. We also need to make sure when we are tokenizing that we are handling multiple languages and accents. We know that India is diverse with respect to the accents they have and the languages that they use. We need to model these into the TTS systems as well. And that is where we have a universal tokenization modeling coming into picture. We want to model different sound patterns, different morphologies, stress and rhythm patterns as well. If we look at the multilingual token tower, we have the base, which includes all the common characteristics across languages, and the subwords. For example, TION is used in multiple word endings, also the and a. The second part, which is the middle, is basically the phonemes or different sounds from languages that sound common. And the third point of the pyramid is basically language-specific rare tokens. Speaking of Whisper's tokenization strategy, it uses a vocabulary of around 50,000 tokens and tries to tokenize using that. It uses audio spectrograms to tokens conversion method. It is like having one giant multilingual dictionary which maps these audio spectrogram bits into tokens of the corresponding languages. Summarizing, tokenization basically breaks the audio into smaller chunks which it can then use for processing. Multilingual tokenization should also involve token overlaps, different dialects, different accents, and different speeds and rhythms that are involved in a particular language. Also, a fun fact, the word count is not equal to the token count. One word can be equivalent to one token. But in some languages like German, one word can be equivalent to 10 tokens. Now that we have looked at tokenization and how these bits are processed, let's take a step back and think how we can turn the speech-based LLM from general to genius. Let us look at some personalization that we can add by fine-tuning these LLMs. Imagine this. You've got a powerful voice assistant. It has been built beautifully and it can answer most queries. Until someone walks in and says, please connect me to the oncology department of the medical laboratory. Here, the LLM struggles to find or recognize this particular medically intensive sentence because it has not seen this. Even though it tries to do a byte pair encoding to put together the words, this word is an out-of-vocabulary word for the LLM. Let's see how the LLM can handle this. Before we dive in hands-on to build something by fine-tuning, let us understand the difference between pre-training and fine-tuning. These speech LLMs are trained on huge amounts of data, and these datasets are generic datasets that are available either in the web or in some books or journals. Therefore, these do not cater to domain-specific examples as we would find in the medical field, legal field, or even in the finance field. That is where fine-tuning comes into picture. We want to take the model and fine-tune it to recognize better these domain-specific information. Think of it like a medical student. Pre-training is medical school and fine-tuning is the specialization. Let us look at how we can do so using a speech-based LLM. What you feed the model matters. There are different datasets that power fine-tuning. And to fine-tune effectively, we need high-quality, domain-aligned datasets. Let us take some example. In the healthcare domain, there are the Mimic dataset as well as the custom EMR notes, and the use case here is doctor-patient conversations. Similarly, for finance, we can use call center logs or even chatbot transcriptions from the use cases of banking assistant. In the legal domain, we have court hearings or deposition transcripts that can be used for legal summarization as well as case extraction. And the last domain, which is very popular, is customer support. The help desk recordings or even the call recordings can be used for issue classification, such as whether the issue is a refund or buying a product, as well as auto replies. Let us look at a demo where we will be fine-tuning the GPT model to our use case. For this demo, we would be using a custom FAQ corpus. You can create your own corpus as a text file and include everything that you need the GPT to learn from. Now, this corpus need not be a huge corpus. It can be something as small as 2 to 3 lines, and the GPT will still learn from it. So I'm going to show you the difference before fine-tuning and after fine-tuning. Here again, we use the GPT-2 tokenizer and we try to tokenize the inputs. Let us say that our text query is, how do I reset my device? So we want to generate a response using ChatGPT for this query. Let us see the difference before fine-tuning and after fine-tuning. So this is where we include our custom FAQ corpus, and we try to train our model for just 500 steps and 10 epochs, and we can see the difference before and after. So when we have a query, how do I reset my device? We see that the response just repeats it and says that if you have a device that is not working, please try contacting us. And now we have trained the model using our custom FAQ corpus, and we see that to reset your device, press and hold the power button for 10 seconds, then release. This is the output, and this is the exact content that we had given in the custom FAQ doc. So here we see that with just 2 to 3 examples, we can fine-tune a model to suit our use cases. These are specifically important when you have specialized domains that you need your speech chatbot or voice bot to work with. Now we move on to the section where we discuss how we can tune or turn the dials to make speech recognition much better. Here we will see how we can control the prosody, the emotion, the speech, and the speed of speech here. We will be covering both the LLM setting that impacts speech processing as well as the settings that control the speech output. The LLM settings that impact the processing are mainly the big 3, which are the temperature, top P, and the repetition penalty. The temperature controls how creative the GPT can get. The higher the temperature, the more creative the response is. If you want to use the GPT for a use case like storytelling, that is what you would use. The lower the temperature, the more controlled it is. If you want to create a voice bot, that is the setting that you would like to use. We also have some real-time trade-offs between latency and accuracy. If you want faster outputs, you go for a good system that is able to produce outputs quicker, even if they are not of good quality. Similarly, if you want a higher accuracy, if you want multiple aspects of the speech signal that is produced to cater to the audience, then you would go for higher accuracy signals and compromise a bit on the latency. We also want to control the speech output, and there are various ways of doing so. Let us say we want to control the emotion, the tone, and the expressiveness. Here, we want to tell the system exactly what is the emotion that we are looking for. We give the cues either in the form of text or in the form of punctuations for the system to understand that this is the output in this particular emotion that the user is requesting. We can also make some prosody adjustments when it comes to TTS because the rhythm, the tone, and the style should match the user's requirements. The same sentence can be told in a formal style or a casual style. So when we go from text to tone, the LLM generates the text and the tags that we provide determines the tone of the TTS. The TTS also interprets emotion from the text and any other context that we have provided to the system earlier. For example, if you want a GPT to always respond excitedly, let us say, then we can provide it in the prompt and expect the TTS responses to show that excitement. The next section, we are going to talk about the AI agents for different speech applications. Let us look at some of the core components of speech-based AI agents. So first, we have our speech interface, which is both STT as well as TTS. Then we have the LLM, which is our core reasoning engine. This converts the raw text or the raw speech into structured formats. The next is the memory and context tracker that uses the prompts that we have provided earlier, for example, the emotion prompt that I was talking about, to redefine the responses. We then also have the tools and action layer, which includes the APIs. We already saw in our labs that we call APIs of 11 Labs or OpenAI. This is where those fit in. And finally, we have the UI or the agent wrapper, which is the voice bot or the chat bot that you're building. The next part of AI agents that we should keep in mind is the prompting techniques and instructions that are given for speech tasks. We can create specific instructions for ASR or TTS and give them as prompts. The LLM is only as good as its prompts are. So make sure your prompts are extensive and inclusive. We are also interested in context-aware reasoning, especially for speech. Given that one word can mean different things and the TTS needs to find out the pronunciation for the word from the context, we want the speech agent to be contextually aware and to use that reasoning before generating the speech. We also have to include the short-term and long-term memory use cases. LLMs are already good at this, and that is the reason why speech-based LLM technologies are so successful. Let us look at some of the applications of LLMs and speech in the real world. The very first would be virtual assistants. These are literally everywhere around us. We have Siri, Alexa, Google Voice, and so many assistants that can control our lives and make our lives better just by us using our voices. We also have customer service automations. Imagine filling out Google Forms just while you speak to the agent. The third one is live captioning and transcription. This is very useful for YouTube videos or videos of courses that you're interested in where you want to take down notes. This live captioning helps us understand even when we don't follow the speaker or there is a problem in the audio of the video itself. We also have language translation and interpretation. A lot of the content right now is specifically in English or even in local Indian languages. But thanks to LLM's fast translation capabilities, we can now view content from one language into another in a matter of seconds. The next and the most interesting one is voice cloning and personalization. Imagine creating your own personalized voice bot. Say you're writing a book, and this voice bot has a context of all the chapters that you have written. And if you want to refer to a character, it can always go back to the chapters and give you an output that matches the characteristics of that particular character. We also have accessibility solutions for speech impairment. Imagine somebody who is hearing impaired. You can now enable them to view any content online because of the live transcriptions that we can generate using a speech-based LLM. In this section, we are going to look at the differences between traditional and LLM-based speech AI workflows. We can see that in the traditional workflow, we have an ASR module, an NLP, and a TTS module. However, in LLM augmented speech AI workflows, we have end-to-end learning, where models like Whisper can be trained jointly on speech, text, and translation. We also have LLMs for unified reasoning. It can reason, summarize, generate, translate, and even ask clarifying questions. We also can integrate retrieval augmented generation, where external information can be included in your LLM for either personalization or domain adaptation. We can also include self-reflective feedback loops, where the LLM can correct itself to generate more harmless and helpful information. Summarizing, we see that traditional speech pipelines are sequential and modular, but LLM workflows are unified, smart, and can be personalized. They can also have a context-rich understanding and can self-improve too. The future of speech AI is not just recognizing, it's reasoning and reflecting too. In this section, we will have a hands-on building of your very own voice agent. So this is a 3-step voice agent architecture. In step 1, you'll set up a speech-to-text system. In step 2, you'll generate a text response. And in step 3, you'll convert the text back to speech. So here we'll be using Whisper to convert your speech to text and 11 Labs to convert your text to speech. We will also record our voice in real time and see how it is being transcribed. We import Sound Device to help us with recording our voice. Here I've taken a 10-second duration for us to record, and I'm going to show you in real time by recording my own voice. Hi, this is a masterclass that deals with LLMs for speech. Now the recording has been saved to myaudio.wave. Now we'll use Whisper to convert this into text. You can give this transcription as input to the LLMs to perform whatever task you desire in your own personalized voice bot. Once the LLM returns us the transcription or the prompt that you have given the LLM, we can now use 11 labs to perform TTS on that output to give us the generated speech. Here again, you can see that the response is saved in audio.mp3, which we will now play.
You said, "Hi, this is a masterclass that deals with LLMs for speech."
You can see that this particular LLM has correctly repeated and identified that I have said this particular sentence in my initial original voice note. So now you have built a real voice AI loop with STT, GPT, and TTS. You can also add personality to your voice bot. You can say in your prompt that you're a wise, clever robot and ask it to respond in that fashion. You now hold the blueprint to creating your own voice agents. In the next section, we will look at how we can personalize these further. So in this hands-on lab, we took real-time audio recording, used Whisper to convert it from audio to text, used GPT to perform whatever analysis we want, and this is the place where you can also personalize your voice bot and create whatever analysis you want the voice bot to do. And finally, we used 11 labs to take the response of the GPT and convert it into speech output. We now saw how to build our own chatbot, but can we make them better? Let us look at how we can enhance speech LLMs with RAG and embeddings. Imagine you are asking your Whisper model, what is the book that I read yesterday? Now Whisper can transcribe this perfectly, but it has no knowledge of which book you are referencing. This is where retrieval augmented generation comes into picture. Here, you can use external databases to improve your model. We can also use embeddings and vector databases in speech. These are specific databases that you can create, and it can be domain specific, it can be use case specific, it can be user specific as well to personalize your own voice chatbots. The voice RAG workflow works like this. The user speaks, Whisper then transcribes what the user has spoken. Then the embedding and search vector database happens, wherein with the embedding of the transcription, the model will try to search the database for similar embeddings. The top 3 documents are then returned by the GPT. These documents are added along with the prompt and other information that the user has provided to the GPT to generate a response. The GPT now generates the desired answer. Once the response is generated, it is passed on to the TTS system, which then generates audio from the desired response. Now that we have smarter and grounded answers, let us look at how we can further better the model by fine-tuning them. When it comes to the speech domain, we want our datasets to be in a particular format for the model to understand and re-evaluate and fine-tune for our specific use case. Let us look at how we can do this. We can see that preparing a dataset for fine-tuning Whisper should look something like this. We need to have the audio waveforms with a particular naming ID, and the similar naming ID should occur under the transcript section as well. So here we can see that 001.wave is the corresponding audio for 001.text. Now the model has a multimodal view into what the text audio pair is. This helps the model fine-tune to our use case and also adapt to the emotion, the context, as well as the out-of-vocabulary words that can occur in our domain-specific use cases. We also want to incorporate some form of reinforcement learning. Just like how LLMs can hallucinate, we want our LLMs to be grounded in the output that they give us. This is the reason why we include a human in the loop. The human now gives feedback about whether it was good, bad, or the preferred response. This can also be used when we are fine-tuning the models, when the user can rate the responses based on whether the fine-tuning has happened well or not. The policy model is also updated. And to update the policy model, you can similarly use vector databases or better prompt tuning. Let's take a real-world example of how RLHF works. In case A, it says, your meeting is in 10 minutes. You have one reminder. Whereas case B says, heads up, you've got a meeting in 10 and there's also a reminder waiting. Now, as a user, we will have a preference towards either a formal tone or a casual tone. And this is where, using RLHF, you can teach the model to respond in a way that you desire. Summarizing, for fine-tuning, we can use models such as Whisper and T5, which are already pre-trained on a huge amount of data, and we can give the data that we want our model to be fine-tuned on. The use case for this is if you want to have domain-specific vocab, for example, in domains like finance or medical, and you want to fine-tune the model to adapt to a particular accent. When it comes to using RLHF to better the model, we have a human in the loop, and the human will then reward the responses to make them more desired. This will lead to better tone, better style, and the right fit. The third part is dataset preparation, which also leads to bettering of these LLMs. Here, we can give the model custom audio and transcripts in order to fine-tune the model to our preference. We've come a long way now. Our AI agent can now transcribe, synthesize, and even chat back naturally. But what is the one thing that's missing here? Our AI agent does not have a memory. It does not remember what your personalized settings are. It does not know you. Let's fix that. In this lab, we will build an AI voice bot with memory. We're going to be giving our speech-based LLM a brain, a long-term memory based on vector databases. Some of the key concepts that we will be covering in this lab are: how can you store and retrieve conversational history using vector embeddings? How can you use a vector database? In this lab, we'll be using the Chroma database. And we will also be deploying a memory-augmented chatbot for your perusal. Here, again, we will be using the OpenAI's API, and we will simulate a chatbot without memory first, include the memory, and see how the chatbot has improved. So here is our ChatGPT, and we will pass our requirements via prompt to the model. We see that we have a user input which says, my favorite color is purple. And we want the response of the ChatGPT for this particular input. After 30 seconds, we ask the GPT model, what is my favorite color? So we can see that response to the first input is, purple is a fantastic choice. It is often associated with creativity, mystery, and luxury. Do you have any favorite shades of purple? It remembers that you told the model purple is your favorite color. However, after 30 seconds, when you ask the same question, it says, I can't determine your favorite color. You could share a bit about your preferences and I might be able to suggest something. However good your transcription is and however good your TTS is, without memory, you have to repeat certain personalizations. Now, let us add memory with a Chroma database. Chroma is a vector database, and we will be adding memory to the chatbot using Chroma. We will store the text embeddings of the user's input and then retrieve them as and when needed. Here we install Chroma, and we also generate the embeddings that are required. So now we are presenting a user fact which says user's favorite color is purple. Now this embedding is stored in the memory. Now let us combine all the parts, right? We want to combine speech to text, memory, as well as ChatGPT. Here again, we will be using Whisper for speech to text. Let us take the transcript, which is similar as before. What is my favorite color? And here you can see that the agent has responded with your favorite color is purple. And you can see here that the context memory is taken from Chroma, the embeddings that are stored in Chroma. If you want, you can add memory on the go also. Let us try adding another piece of memory to our chatbot. Let's say the user lives in Delhi and see if the chatbot can remember this and retrieve this information. Once we have added the information to our Chroma database, we now ask the query, where do I live? And the agent responds by saying, you live in Delhi. In this tutorial, we have learned how we can create a smart chatbot by integrating memory so that it remembers your personalizations and gives you the desired output. Summarizing, without memory, we just have a chatbot, the user queries the chatbot, and the chatbot responds. With memory, we have a vector database lookup, and once the response is generated, we then use the LLM to compare the database and the response and find similar embeddings and include these as a prompt for the TTS to generate the desired response. In this section, we are going to look at how speech AI behaves in the production scenario. The very first thing that we need to take care of when we deal with speech AI agents in production is observability and monitoring. The systems keep changing, the inputs keep changing, the data keeps changing, and therefore we need to adapt our model to this changing landscape. And to identify when our model is not behaving well, we need to have some form of observation pipelines. We will look at some of the things that we need to track to identify when our model needs to be updated. What to monitor in a speech AI system? So when you're talking about speech to text or automatic speech recognition, one of the most important metrics that we look at is the WER, which is the word error rate. Here, we look at the number of insertions, the number of substitutions and deletions as compared to the total number of words in the output and come up with the word error rate for a particular utterance. We also look at confidence scores per token. How confident is our model in predicting that a particular feature corresponds to a particular token? We also have other audio quality metadata that gives us insights on how well the transcription is taking place. For the NLU or the LLM part, we have intent classification errors where a particular utterance corresponds to one intent but is being classified as something else. We also have hallucination detection. We know that LLMs are very creative and they can start to hallucinate facts, which is not desirable. So we need to keep track on that particular aspect as well. We also have the prompt drift or output variance that we need to look out for. In terms of text to speech, we need to quantify how naturalistic our machine-generated speech is. So we need to look out for pronunciation issues, prosody mismatches, as well as lag or latency spikes when it comes to generating speech. As I said, data is always evolving, and so is your personalization. You may have liked something else 2 months back, but now your favorite movie is something else. How can the LLM adapt well to this? We need a continuous model update and adaptation process in place to take care that the model adapts to the personalization changes or to the domain changes as well. We also need a continuous learning pipeline wherein we are pumping in new vector databases as and when they are appearing. For example, a movie could have been released in the recent past and we need to include the review for the movie for a movie review voice bot. We see here that the live input depends on real-time metrics and we have to have regularly scheduled retraining for the speech model. And this itself is a loop apart from the other loop, which is basically the feedback loop and the data store. This brings us to the last section, which is basically the advancements in the speech AI domain and also some of the considerations that we should be aware of. We can see that we have come a long way in speech, starting from recognizing 0 to 9 to building multilingual real-time translation agents. We can see that we can just take German speech and convert it into a Portuguese output. You can see that the speech goes into Whisper and then converts to English text, uses GPT Translate, converts to Portuguese text, and finally uses the voice TTS to give the output in Portuguese. We can also build hyper-personalized voice assistants. It can sound just like you or anyone else as well. However, there are some ethical considerations and challenges that we need to look at. For example, there are a lot of deepfake risks and cloning problems that we may encounter. Imagine someone sounding like your mom and giving you an emergency call. We do not want that, right? So even though the original voice and synthetic voice is so similar that even a human cannot make out the difference between the two, we need to be very careful in the applications and be ethical in making decisions with respect to where we want these chatbots and voice bots to work in. We also need to be considerate about the bias in speech recognition. Given multiple accents and multiple dialects, we want to be as inclusive as possible and reduce the bias in our speech AI agents. When we see the timeline of speech AI progression, we see that starting from keyword spotting in 2010, we've had smart assistants in 2018, we've had emotional and multilingual STTs in 2023, and now we have personalized, expressive, multilingual chatbots that can synthesize speech in your own voice in 2025. Let's walk over everything that we've learned in this masterclass. We started with building our own voice bots, using Whisper to translate real-time recording of our voice into text, fine-tuning them to our preferences, personalizing them, and finally, including memory so that the chatbot remembers your personalizations. Overall, we also looked at the different pillars, STT, TTS, and how all of these components hold together to create your very own personalized voice bot. Speech is human, and AI that understands speech has the potential to break barriers and connect cultures. But it also creates real risks. So we should be very careful of how we are formulating it. So let's build accessible, accountable, and inclusive speech AI systems. I call all of you to explore this space and build your very own personalized AI agents that can speak your language and understand your emotions. Thank you for watching this masterclass.